This is a continuation of the Chapter 4 review tutorial with Problem 12. Problem 12 says, graph the segment xy with endpoints x 5, -2 and y 3, -3 and its image after reflection in the x-axis, then a rotation of 270 degrees about the origin. This is a composition, this time with a reflection followed by a rotation. So let's go ahead and write our points and figure out what our transformation is going to look like. Now, a reflection in the x-axis is just like all reflections in a line. The point is going to move along a line perpendicular to the line of reflection, and it's going to move a distance equal to the distance from the pre-image point to the line of reflection. So this point is 2 units below, it's going to move 2 units above. This point is 3 units below, it's going to move 3 units above. Now there was a transformation notation for that particular type of reflection, and that transformation notation was x, y, goes to, the x stays the same and the y changes sign. So it goes from negative to positive. So the x stays the same and the y changes sign. So our new points here, x prime, the x stays the same and the y changes sign. 5, 2. Y prime, 3. The y changes sign. 3. So our new point is going to be 5, 2. So 5, 2 and 3, 3. And there is our x prime, y prime. Now, for a rotation, 270 degrees about the origin, what we're going to do is we're going to use the transformation that we used in the last problem for a 90-degree rotation about the origin, counterclockwise. It doesn't matter whether we go clockwise or counterclockwise with this one, so we're just going to go counterclockwise twice. So the transformation notation for that one, let's go back to our original color, and the transformation notation will be x, y goes to negative y, x. This is a 90-degree counterclockwise rotation. So our x double prime then, so x double prime is going to be negative yx. So the y goes negative and becomes our new x, and our x becomes our y. Now as you can see, we're rotating our reflected point. We're not going back to the original. So our y double prime then is going to be negative y x. So negative 3, 3. All right, and that point, let's use this color. So we have negative 2, 5. So negative 2, 5. And negative 3, 3. Negative 3, 3. and that becomes our final segment. So here was a reflection and then a rotation of 270. Now we're going to do it again because this point has to go to 180 degrees. So we're going to do this again for 180 degrees. So let's go back. And this time our x triple prime is going to be negative yx. So negative 5 and negative 2. And our y triple prime is negative yx, so negative 3, negative 3. This gets us 180 degrees. And then we're just going to write x to the fourth. It's not an exponent, it's just the fourth iteration. So x to the fourth is negative yx, 2, negative 5, and y to the fourth is negative yx, 3, negative 3. So our final implementation, we'll use this strange color, will be 2, negative 5. So 2, negative 5. And 3, negative 3. So our final image point is going to be over the top of our original image point. And there is your final transformation. So it went rotation, rotation, rotation. So this is your final point, your final figure from your original pre-image after the composition. And now we'll move on to problem 13. Problem 13 says, determine whether the figure has rotational symmetry. If so, describe any rotations that map the figure onto itself. So a figure has rotational symmetry if the figure can be mapped onto itself by a rotation about its center of an angle of 180 degrees or less. So let's take a look at this figure. If we were to draw lines through these, that's not a very good color. Let's go back to this one. That's pretty good. And then a line through this, and then a line through this. We can see that the figure seems to be symmetric about each one of these lines. So what we have to determine is if these angles are less than 180 degrees. So in this case, we have 1, 2, 3, 4, 5, 6. So there are 6 points in this figure, and if we want to compute the angle between these two figures, we take these 6 points, and since the distance around goes 360 degrees, 360 divided by 6 gives us this angle inside here. So this angle then would be, let's change this back. So this angle is going to be 360 divided by 6, which is 60 degrees. So yes, in fact, this figure has rotational symmetry, and it can be mapped onto itself by a rotation about its center of an angle of 60 degrees, 60 times 2, which is 120, and 60 times 3, which is 180. So we can map it angle equals 60, 120, and 180 degrees. Now to problem 14. In problem 14, we have a pentagon. It has 5 points. So to determine if this has rotational symmetry, we would take 360 and divide it by 5. 360 divided by 5 is 72. 72 degrees. So yes, in fact, this has rotational symmetry, 72 degrees, and 72 times 2, which is 144 degrees. So you would say yes, 72 degrees and 144 degrees. Now on to problem 15. In problem 15, we're told to describe a congruence transformation that maps triangle DEF to triangle JKL. So DEF is here, -2, -1, 4, 1, 1, 2, and JKL is -2, -4, -4, -2, and -1, -1. Now, it might be difficult to see, but if you notice, this point is 1 unit to the right of the y-axis. This point is 1 unit to the left. This point is 2 units to the right, and this point is 2 units to the left. This point is 4 units to the right, and this point is 4 units to the left. So it would appear that you could reflect figure DEF about the y-axis and have the same orientation as JKL. Now, if we were to do that, we would have this figure. So we would have D prime, E prime, F prime. Now, as it appears here, so all we really need to do is move this point down 3 units, this point down 3 units, and this point down 3 units. So in words, what we can do is reflection in the y-axis followed by a translation 3 units down. Now for problem 6.